This is the structure of the command pattern in a UML diagram. It may look a little complicated at first, so let's dig into it piece by piece. Top left is the client. This is the part that wants to get something done. For the command line order processor, that would be you or me sitting at the keyboard. For some application with lots of bells and whistles, the application itself is the client. Next to it is what we call the invoker. This component asks the command to perform a request. In the command line order system, this is the main program. Bottom right is the concrete command. It knows how to perform the action requested and may enlist the help of a receiver object, or may go it alone if the action is simple enough. In the command line order system, there should be a concrete command for every command in the system. The receiver could be a separate object or just a method in the concrete class, depending on the complexity. The concrete command fully encapsulates the command so that the client is no longer concerned with the particulars. The undo method is optional, though it is frequently found in many applications. Think of a Python IDE, for example, where undo is usually available from the Edit menu. Okay, so what do we get by following the command pattern? One important thing is that the commands are encapsulated in separate concrete command objects. Each one knows how to process its command, and that's all it needs to do. Note, though, that the client doesn't pass in arguments to the execute method. That information is hidden and allows the client to invoke any command without knowing any details. It's also easy to add new commands to the system. Just write new concrete commands. That means we're following the open-closed principle. Remember the original command executor class? We'd have to open it up to add or remove or change any of the commands. Okay, so now we're going to look at how to do this in code. We're going to re-implement the order processing system to produce the same results as before. This time, however, we're going to use the command pattern to do it. To put it all together, we'll then rebuild the main program, which is the invoker in the UML diagram, to use the new pattern. In the command project in PyCharm, we can see the pattern begin to take shape. Here is the abstract base class for the concrete command objects. It declares the one required method, execute. Note that we're not adding undo support at this time. There's also a second abstract base class, the abs order command, which we'll use as a mix-in to add additional properties to the concrete commands. This will require us to implement name and description values. Notice also in the project window that there are separate modules for each command: create order, update order, and ship order. There's also something new, no command, to which we will return in a moment. As before, I've only implemented the update order command. Note, that includes implementations of the abstract properties name and description. You might be wondering how this works without using the property decorator and a method definition or two. Well, the Python abstract base class machinery only checks that something is implemented in the concrete class. It does not check that the implementation matches the declaration in all aspects. Indeed, in a dynamic language, this could be quite costly at runtime, and may be impossible in some cases. But here, this actually serves my purpose, since what I want is constants assigned to those properties. You'll see why in a minute or two. The update quantity class goes on to define the required execute method, which looks much the same as before, except that the new value has moved to the dunder init method. This is required in order to expose a parameterless method to the client. So, let's look at how the main module uses this pattern. To start off, it imports all the concrete command classes that have been defined. Now you may be thinking, doesn't this violate the open-closed principle? Well, yes, actually it does, since we'd have to change the main program for changes to the command suite. However, this could be easily overcome by putting all the concrete commands in a separate package and then loading whatever commands are found there at runtime. Now, using the concrete command classes, the getCommands function builds a dictionary where the keys are the names of the commands and the values are the class references. This is what we wanted to use that name property for. There's also a new function, printUsage, that is used when no commands are supplied. However, in this case it uses the dictionary created by the getCommands function and that description property. The parseCommands function uses the setDefaultDictionary method. This method looks up the command supplied, which is in arg0, in the dictionary. If found, it returns a reference to that class. If not found, it returns a reference to the noCommand class. And here's what that one looks like. What it does is saves the command entered, whatever it is, and then when the execute method is run, prints an error message and exits. This is an example of another design pattern, the null pattern. Using this pattern means that the caller does not have to check for null results, or for none in Python. The caller can simply use the object as is, since it implements the required methods and properties. It's hard to emphasize how useful this pattern is. Code can be much easier to read and write if we can dispense with null object checks. And this is exactly what the null pattern gives us. Back in the main program, the parseCommand function returns a new instance of the command found, or noCommand. All the main program has to do then is execute the command. So let's run it. Our program works. The quantity has been updated to a value of 42, which Douglas Adams calls the answer.